All right. Now we have the idea. We need to implement it. So we need to fix all the details. So the idea is sort the array R times digit by digit, because we know the largest integer can be represented in R digits. So we can sort digit by digit. Okay. All right. So question, in which way should we sort? Okay. Yeah. So there are many ways we can sort. In which way should we sort? Right? From left to right or from right to left? Yeah. So we really need to compare those two ways. Yeah. So the first question we need to answer. Yeah. A, from the least significant digit to the most significant digit. So that's from right to left. Least to most. B, from most significant digit to the least significant digit. So which way you think better? Okay? Better means it should be correct first. Yeah, better here, not meaning faster, meaning correct. Okay, yeah. Sorting in which direction? Now, we try to do some analysis to understand which way is better. Yeah. All right. First question is we want to know which digit has the biggest impact on the ordering of the array. Biggest impact. Which digit? The least significant or the most significant? Biggest impact. So you can guess, yeah, probably the most significant, right? Because from its name, most significant. So that's related to the impact, also most, the biggest. Yeah, but let's see, why is that? All right. Suppose this is the general expression of our integer, using the general base D, general, okay, yeah. Then the most significant, so we know which one is the most significant. All right. Here we compare two ways, digit-based sorting. A way, 1, 2, 3, 4. So that means 1 means the first time, yeah, we sort in this order from the least significant digit. Second time, the third time. So the most significant, the last time. n+1 time. Okay. B, in this way. First time, most significant, then second and third, and last. So we want to know which one can give us the correct result. Yeah. When we sort the array based on the current digit, here the question, is the order from the previous sorting preserved? Because every time when we sort it based on one particular digit, there is an order. Okay? The next time we sort based on a different digit, do we preserve the order from the previous sorting? That's the question. Yeah. Based on our intuition. So here, yeah, intuition is important. When we do thinking, most of the time we're based on our intuition, right? So based on our intuition, the answer seems more likely to be no. No. How can you preserve the order of the previous sorting? So in general, the answer is no. Okay? So because you cannot preserve order from the previous sorting, then let's look at the which way is better. Okay? Sorting based on which digit gives us the biggest impact for the final order. Biggest impact. Sorting based on which digit? Yeah. All right. Think about this. When you sort based on this first least significant digit first, so you get an order, but the second one based on that, but the order you get from previous one changed, must be changed. Then next one must be changed. Then next one, then all the previous order all changed, right? Then the last one. The last one, you know, based on this digit, it must be in ascending order. But for others, you don't know. Okay, so that's the first one. Similarly, when you do this, the first time you make numbers ordered based on the most significant digit. The second time based on that, but then the order will be changed. Okay? Then you do, finally, when you do the last time, all the order you did before all changed. So which one you feel as a final result better than the other? Better than the other. Compare the last sorting in both cases. The last sorting in A based on this. The last sorting in B based on this. Which one you feel closer to the correct answer? The last sorting based on the most significant or the last sorting based on the least significant will give us the order that closest to the answer we need. Definitely the most significant one. Okay? Not the least significant one. Least significant, you know, because it has the minimal impact to the whole order, right? The least minimal impact. That the most significant, it has the maximum impact. This has the minimal impact. Definitely you want to pick the maximum impact, right? Yeah. That's why we should pick the A way, not the B way. Okay? After this analysis, we know we should pick the A way, not the B way. So we start from the least significant, then the last time the most significant. So that is important. After we fixed this critical problem, when we can go to the, next step. Conclusion. Although there is a chance to be sorted, it is not guaranteed. Yeah, but because we still were not quite sure if the whole array is sorted or not. We just feel by our intuition, A way will give us closer to our final goal. That's what we get from A. B, far away from our goal. Okay, so that's what we get here. But we still not get to the point we like to be. Okay, so let's go to the next step. What kind of order preservation? Let's study the order preservation. Yeah, because we may need that. All right. The fact is, order based on the current digit would not preserve the order from the previous digit. So definitely, so you cannot. Yeah. So, but we must preserve something, right? It's not nothing, something. Although not the whole thing, but something. Yeah. That's what we need. Yeah. Why we need to preserve the order from the previous digit? Are we asking too much? That probably too much to ask for. Yeah, we should not ask that much. Okay, yeah, but we need a weaker requirement. Let's make our, requirement weaker a little bit so we can get there. Yeah, we do not need global order preservation. Global. Whole array, previous order, the whole preserve. No, we cannot. Okay. That's the global preservation. We don't need it. Too strong. Okay. we just need local order preservation. Local. What do you mean local, right? Local order preservation. So we make our requirement weaker, but what's the meaning of local order preservation? Yeah. It is order within the same digit. Okay? Yeah, because only when the current digit same, so A here, A also here, right? Within the same digit. Yeah, let's look at another A, okay? All right, 3 numbers. Then order from the previous digit preserved. That's the local. Yeah. Under the condition, the current digit, the same current digit. That condition. Under that condition, if the order is preserved, then that's enough for us. Okay. That's our analysis. So when we have this point, then next it will be much easier to get the whole array sorted. All right. Now, local order preservation. That is within the same current digit. The order based on the previous digit is preserved. The same current digit. So I, draw that diagram before. Yeah. So, but here the problem is, do we have such sorting algorithm that can satisfy this requirement? That's the key question we need to answer. Yeah. Not every sorting algorithm has the above property. Some algorithms may have, but some may not. So we need to investigate this problem. So fortunately, the counting sort has this property. The counting sort has this property. Nice property. So we can apply the counting sort here. So the conclusion, yeah. So why counting sort has it? Yeah. So next slide we will take a look a little bit. The counting sort can be applied at each digit in the radix sort. That property, the sorting algorithm with that property. So there is a name for it. Okay? The name is stable sort. Stable sort. In one of my previous comprehension questions, I remember I asked you, so if the quicksort is stable or not. So at that time, I don't know if you understand this or not. I have some impression in class, I mentioned this stable concept a little bit. I remember, before the lockdown, I remember in the class, I talk about the stable algorithm a little bit. Yeah, so that's why I ask you the question about the quicksort. Yeah, but here, so I may feel, so many of you may not have strong impression on this concept. So let me explain it another time. Stable sorting algorithms. The definition. The numbers with the same value appear in the output in the same order as they do in the input array. Same order. So let me use a diagram to explain it. Yeah. Otherwise, you may not get a clear understanding. Yeah. Suppose the input like this. We look at arbitrary. So let's look at 2 elements with the same value. Yeah. Here, the same value is important. When you have the same value, when you sort the whole array, because you have 2 ways, right? AI first, AJ next. That's one way. But AJ first, AI second, another. Both legal. Both we treat sorted because they have the same value, right? So which one is at first? It does not matter, right? But actually, it matters. It matters. So we need to really use some concept to describe these two different cases. Okay, yeah. The output. All right. So suppose we have two elements with the same values in the original array. Then we apply a sorting algorithm on it. So you get a whole array sorted. But in your sorted array, check the elements again. Is the AI before AJ or not? If AI still before AJ, so that means the order preserved from the original order. The original AI before AJ. After you apply some sorting algorithm, you have the same order. That means it is stable. The other way, the opposite way, you switch the order of these two elements, not stable. So same order, way, stable. Different order, way, non-stable. That's the concept. Okay? Because when we saw digit by digit, this stability property, extremely important. If it's not stable, when you apply, the order you have in the previous step messed up, completely messed up. So you do not allow that happen. So that's why we need a stable sorting algorithm. The counting sort is stable. Why the counting sort is stable? So next slide I will explain that. Yeah. All right. So now examine known sorts stable or not. Okay. So here let's look at the reason why we get stable, non-stable. What is the main reason? Key reason. After we know that, then we can easily check if an algorithm is stable or not. A sorting algorithm is stable or not. The main reason related to the swap operation. The swap operation may change the stability. May change. Not always change. May change. Sometimes it could change. Sometimes it won't change. Okay? So what time? So think about this. All right. Because there is example, the bubble sort. The bubble sort, we do a lot of swap, right? Swap operation. But the bubble sort, when we do a swap, we apply it on two adjacent elements. So in that case, we won't change the order. Because the two adjacent order, only the first one is greater than the second one, we do the swap, right? But the first one equals the second one, we don't do the swap. So you can see for the bubble sort, we won't change the order to the opposite way. So the bubble sort, although we do swap, but we do adjacent swap. If you do adjacent swap, you won't change the order. All right? But if a sorting algorithm may do non-adjacent swap operations, then it is very likely, so we will see in general case, it is not stable. It is not stable. Okay, non-adjacent swap. adjacent swap, it is fine. Adjacent swap and no swap, the algorithm will be stable. Non-adjacent swap, the algorithm will be non-stable. Okay, or unstable. Yeah, just, that kind of word. Yeah. All right. Now let's look at the, so here, non-adjacent swap, not stable. Yeah. So let's check these algorithms. First, the selection sort. Is this stable or not? How do we do selection sort? Okay. Each scan, we try to get a minimum of the current subarray. Subarray for those elements that have not been placed, have not been put in place. Okay? Current subarray. So we get a minimum. All right. After we get minimum, we put that minimum in place. Right? In place. The question is, how do we put that element in place? How do we put that element in place? Okay. Do you need a swap operation? Think about that. Do you need a non-adjacent swap operation? Yes, right? Yeah. So you need a non-swap operation. So it is not stable. Right? Next, insertion. Insertion, we do not do any swap, right? No swap. So we are safe. So it is stable. Merge, we do not do any swap, right? So it is stable. Yeah. Quicksort, we need to do swap, and it is non-adjacent swap, right? Non-adjacent swap, long distance swap. So it is unstable, right? Counting, we don't do any swap, right? Counting, think about the counting sort. Do we do any swap? We don't do it. Okay? Yeah. So now you can see, with this concept, we can easily check if a sorting algorithm is stable or not. Okay? So then, for the situation like this, digit by digit sorting, we want to preserve the order, with the same current digit. We need a stable one, so we can comfortably, we can pick counting sort. All right, so that is part of B.2. Next, we will see an example. So we need to apply the radix sort. All right.